Yeah, good evening guys. So please type in the chat box. Am I audible? Yeah, so please type in the chat box. Is the audio and video clear to all of you? Yeah, all clear. So let us start this session. So this is lecture number 8 in this refrigeration and air conditioning part 2. Okay, so in last class, I'll just give you a quick glimpse of what we have done in last class actually. So in the last class, we are talking about the concepts of intercooling and reheating, intercooling and reheating in Brayton cycle. In Brayton cycle, then we also have concept of regeneration, We have discussed these things in a much broader sense, and we have solved certain numericals of Brayton cycle. And also in last class about refrigeration, we have seen the definitions of refrigeration and air conditioning, correct? Refrigeration and also air conditioning. And we have seen this refrigeration and air conditioning, then we have seen the concepts of refrigerators basically from Clausius statement, refrigerators and heat pumps. Okay, so we have seen how to calculate the COPs and all the stuff. In case of reversible cycles, how to add them into the reversible, how to convert this heat interactions in terms of temperatures. And also we have seen units of refrigeration. I have shown you that as well. So units of refrigeration. So this units of refrigeration, we have seen 1 ton of refrigeration actually. 1 ton of refrigeration, which gave us something around 211 kilojoules per minute. I have shown you. Basically, this is the amount of heat equivalent to producing 1 US ton of ice in 24 hours. Okay, from 0 degrees Celsius of water to 0 degrees Celsius ice, and this is also equivalent to 3.5 roughly kilowatts. Okay, so 3.51, some books say 3.51 and 3.49 kilowatts, whatever. In last class we have seen the calculations. Okay, so these are the things that we have seen in the last class, and in today's lecture we will start looking at the things which is vapor refrigeration systems and also gas refrigeration systems. Of course, gas refrigeration compared to vapor slightly a bit less, and we'll skip we'll go into the air conditioning. We'll try to study properties of moist air, and also we'll solve some numericals at this point, and if time permits I'll also continue with psychrometric process and chart today, or else maybe we'll deal this in the next class. Okay, in the tomorrow's class. I'm sure till here we'll also see a bit of properties of moist air, but this psychrometric process I'm not sure whether time permits or not. If time don't permit, I'll teach you in the next class. Okay, so this is the plan for today. Is that clear to all of you? Okay, so please type in the chat box. Is this clear to each and every one of you? Are you all clear till this points? Till this points in this course? Okay, so shall we start today's? Yeah. Now let's see vapor refrigeration systems basically. So how we do this vapor refrigeration systems is clearly, look, basically if you see, this vapor is the working fluid, or basically you can say, instead of writing working fluid, the phase of substance in during refrigeration. Okay, so this is the phase of the substance during the refrigerations. Now what we actually do is, look, the basic idea here is, let's say if there is some refrigerated space. Okay, so there is some space which is actually refrigerated space. Now the job of your working substance is basically, let's say there is a coil which is passing like this through the refrigerated space, and in this we have some liquid or basically some fluid. I would like to say fluid because phase transition happens during this point. So phase transition happens, so therefore this is liquid plus vapor, and normally by the time it completes here we'll get complete vapor, and here it's liquid in general, and this is the refrigerated space. Now clearly what happens when this cool refrigerant is flowing, definitely if this is T of the refrigerated space and this is TL of the refrigerant, then definitely TL will maintain TL such that this is less than T of this refrigerated space actually here. Okay, so this is T of the refrigerated space, then we will try to maintain this L or TL less than this T refrigerated space. Then what happens when these two get in contact with each other? Definitely if there is some heat or there is some temperature difference, heat starts flowing into this, yes or no? So that's how this working fluid will actually take out the heat from this space and it will try to maintain this space at T refrigerated space. Did you all get the idea how we are maintaining the cooling here? Look, try to understand. Through this pipe, what happens? Fluid actually flows, and when this fluid is flowing, the temperature of this fluid is maintained less than this refrigerated space temperature, so that heat actually flows from this space to the liquid actually, and this space is maintained cool at that particular point. Clear? Did you all understand this? Now your job is how to continuously supply this liquid. That's the main important part. Okay, and also when you are supplying, the temperature of the liquid must be much less than this T refrigerated space. These are the two conditions that you have here. Okay, now you can see, if you see a device basically here, practically how do you bring this TL to low temperatures? That's what the main important thing. So TL is maintained by these devices. You have this evaporator, because in this evaporator coils, this fluid actually flows and the fluid converts from liquid state to vapor state. So evaporation actually happens in this device. Okay, then if you want to rotate this, if you want to circulate this fluid in a circuit, at some location, if you are evaporating this fluid, then definitely at some location you should also condense this fluid. So you have a condenser where actually heat is coming into the evaporator, means heat is coming into the working fluid at this point. So let's say this is QL, then definitely heat should go out of the fluid at this point. Okay, so working fluid is the main substance. So at this particular coil, working fluid is undergoing evaporation. So definitely at some other location, working fluid should also undergo condensation if you want to repeat this circuit. Okay, and then you can see definitely these condensers operate at some pressure and evaporators operate at this pressure. Now you have something called pressure increasing mechanism, and also pressure decreasing mechanism here. Pressure decreasing mechanisms. So you can connect the circuit now clearly. You can see this is how it happens. So this is the circuit actually. The fluid flows like this, and the refrigerated space will be in contact to the evaporator actually. Okay, so this is the refrigerated space, and this coil, whatever is the in which the fluid is flowing, that's called the evaporator's coil actually. Okay, so this is the evaporator coil. Now in this case, when you're dealing with vapors, depending on this pressure increasing mechanism, we classify the systems into two types in general. In case of vapor refrigeration systems, VCRS, vapor compression refrigeration, and also VARS, which is vapor absorption refrigeration systems. Okay, so if you see, if PL to pH, if the vapor is taken from PL to pH by means of compression, means let's say you will directly put a compressor and you will take the system from PL to pH directly by compressing it. So that's called, if this is by the means of compression, then we get vapor compression refrigeration systems, VCRS, which you all know. If this PL to pH is by means of absorption, then we get VARS, vapor absorption refrigeration system. Okay, so we see two basic things here. This C is for compression and this A is for absorption. Vapor compression refrigeration systems and vapor absorption refrigeration systems actually. Okay, now first let us have some idea on this VCRS, then we'll eventually go to VARS, and then after gas refrigeration cycles. Okay, now VCRS, look, vapor compression refrigeration systems. Let us have a look at this. Vapor compression refrigeration systems. Vapor compression refrigeration systems. Okay, now let's see. So ideally, we know Carnot cycle is the best cycle with having the best COP. Now if you see reversed Carnot, okay, let's start investigating reversed Carnot cycle. First of all, reversed Carnot cycle. And since we are dealing with vapors, let us consider the dome, vapor dome. TS, let us say. Of course, refrigerants will have different shape of domes. This is again dependent. Now let's see, we need two pressures. One is pressure of the evaporator and the other is the pressure of the condenser, P condenser actually, P condenser. So clearly we know Carnot cycle has the best efficiency, so definitely reversed Carnot will have the highest COP. Okay, so let's try to construct a reversed COP, reversed Carnot cycle. So let's say first I'm drawing the things. So let us say here you have the system something like 1, 2, 3, 4. Okay, and the saturation pressure or saturation temperature corresponding to P evaporator is TL, and this point is TH actually here. Okay, so this is your TH. Okay, so this is TH. Now, so clearly this is a Carnot cycle, reversed Carnot cycle, of course. So this is your reversed Carnot cycle, and this cycle undoubtedly has the best COP because the reverse of this cycle is nothing but your Carnot cycle having the best efficiency. Okay, now let's see this cycle, even though it has the best COP, but practically there are certain issues in dealing this cycle. You can easily manage this 4 to 1 and 2 to 3 this time because the phase change happens definitely at the constant temperature, and to this cycle, you know, heat addition is happening at this point QL, and heat rejection QH is happening at this point, because you see in the condenser we have the heat loss, because if the working fluid has to come back from vapor phase to liquid phase, the working substance should reject some heat. So heat goes out of the cycle in this device, which is the condenser, and here in the evaporator the system actually takes in heat. Okay, system is nothing but your vapors, okay, or liquid, whatever is the phase depending upon, basically your refrigerant. Now see, this is QL and this is QH. So heat addition and heat rejection can be made isothermal, it's very easy, but this process 1 to 2 is very difficult because practical difficulty in reversed Carnot. Practical difficulty in reversed Carnot. You got certain practical difficulties here. Is 1 to 2 is a two-phase substance. Is a two-phase substance, and clearly the dryness fraction of this substance is low compared to the superheated. Here this is a two-phase mixture, so practically using a compressor for this two-stage mixture is not very easy. Okay, so therefore if we are dealing the compression systems, now your job is to compress this substance from location 1 to location 2, and obviously isentropic compression is the best. But when you are trying to compress the system from state 1 to state 2, this is a two-phase mixture, and the dryness fractions in this level is not very much high. So definitely, they are high but not very much high as 0.9, 0.95 of that range. So clearly it is difficult. Is a two-phase compression. Is a two-phase compression. So clearly compressors cannot. Compressor health is or compressors, or basically you can say it is not safe for compressors. So it is not safe for compressors. It is not safe for compressors actually. For compressors, because we see whenever there is certain rotating set of blades, then definitely this having high amount of water vapor in the substance is not very good for the devices, like we have seen in the case of a Rankine cycle, and same logic here. So basically this process cannot be done easily. Okay, and also you can see 3 to 4 for expansion. If you use a turbine, because you have to bring down the pressure from 3 to 4, since turbine is not economical because specific volume is very low during the process 3 to 4, during the process 3 to 4, correct? Because if you put a turbine, actually blade erosion will happen in this particular case because of 1 to 2, and in case of 3 to 4, since specific volume is very low, if you calculate the work interaction minus integral VdP, this V is very low actually. So practically you cannot use a adiabatic turbine to get this particular process 3 to 4. So that's why practically, even though theoretically this suggests the best COP, but practically there are these two major impacts because of which you cannot actually rely on this cycle. Is this clear to all of you? Yes or no? So please type in the chat box. Can you all understand why this cycle cannot be practically put into use because of these two constraints? Okay, clear to each and everyone. Loha, Sukumar, yeah, Ankit, Mudit, Vivek, Vishal, every one of you. Okay, clear? Now let's try to understand. You may have one doubt. Of course, this issue is still there, but you may have asked me one more thing. Instead of stopping this point here, I would have constructed one more Carnot cycle. Look, I would have stopped this point here. I would have done this cycle also. Okay, so let's say this cycle is, for example, your 1 dash, 2 dash, 3 and 4 again. Okay, so 1 dash, 2 dash, 3 and 4. So let's say this is the cycle that we are using. 1 dash or 1 dash, 2 dash, 3, 4, 1 dash. So this is also one more Carnot cycle. This is one more Carnot cycle. Carnot cycle actually. In this case, of course, 3 to 4 may not be addressed, but this 1 to 2 dash problem is avoided now. Yes or no? Basically, whatever the problem you have now here because of this blade erosion, now that gets eliminated because it is completely a dye vapor. Okay, but the practical difficulty in this is, if you see this pressure which is passing through this, so this pressure is P intermediate pressure. Okay, so this is P intermediate pressure actually. Okay, so this point 2 passes through some constant pressure curve which is intermediate between this evaporator and condenser. Okay, now can anyone tell me this part of the compression, actually your compression is 2 dash, I mean this heat ejection is 2 dash to 3. Now can anyone tell me what is this process 2 dash to 2? This part of the process 2 dash to 2. 2 dash to 2 is actually isothermal compression. Isothermal compression actually. Okay, so 2 dash to 2 is isothermal compression because you see at constant temperature you are increasing the pressure of the system from 2 dash to 2, and clearly 2 is the point passing through P condenser and 2 dash is the point passing through P intermediate. P condenser is definitely greater than P intermediate. Okay, so this part of the heat rejection 2 dash to 2 is actually isothermal compression. So definitely you feel it difficult. This is difficult to achieve. This is difficult to achieve actually. Okay, so this is difficult to achieve. Clear? So that's how all the two possible, sorry, PV is equal to PV. It is isothermal, right? It is isothermal compression. So this part of isothermal compression is not very easy to achieve. That's why these two possible Carnot cycles are eliminated here. So we cannot actually design a system running with the help of Carnot cycles. Clear to all of you? Did you all understand why this outer Carnot cycle is also not possible because of this difficulty? Okay. So please type in the chat box. Is it clear to each and everyone? Come on, quick. Nitin, Sukumar, Mudit, Loha, Yogesh, Ankit, Vivek, Aspirant, all of you. Sukumar. Clear? Now, let's see. So if this part, so clearly one thing is very much clear. You cannot do this process. So one possibility is this. If you can eliminate this 2 dash to 2 as constant temperature, then definitely you can make this cycle possible. But again, one very important issue is this: installing a turbine at this location for expanding the system from pH to PL is not very convenient. Okay, because you see this V is very small. So actual cycle what we use is, this cycle needs two corrections. One is this part of the process has to be replaced. Second, 3 to 4 isentropic expansion in a turbine is also not economical. So this cycle, this outer Carnot cycle, means this cycle, it needs two corrections. 2 dash to 2 process should not be isothermal. Secondly, this 3 to 4 should not be in a turbine, in an adiabatic turbine, of course. Okay, because installing a turbine cost is very huge, but the power it generates will be very small. Okay, so that's why it's not very economical. So doing these two corrections, we get this standard VCRS. Standard VCRS, and the cycle what we use here is reversed Rankine cycle, which is also called Evan-Parker cycle. Normally in ESC and all, you can have certain good idea of this, but you can see this is also the reversed Rankine cycle. The problem is at these two parts, 2' to 2 and also this expansion. So what we do is, see, if you have this diagram, temperature versus specific this entropy S. Now if this is the dome that you have here and you have this pressure P evaporator, sorry, okay, and this is entropy S, then you have this P evaporator, and clearly P condenser. You have this P condenser. I think just a minute, sorry, we can elongate it like this better. So this is P condenser. Now what we do is, the substance which is here, with the help of a compressor, now it's completely superheated, you go till this point, okay. So 1 to 2 is the compression. Now you can do it in a compressor because completely it's vapor. Since this part, instead of doing it isothermal, because you are feeling it difficult at this location, rather than doing isothermal, we do the heat rejection at constant pressure. So in the condenser, at condenser operating pressure, what we'll do, we will actually do this heat rejection in a 2 to 3 in a constant pressure, okay. So 2 to 3 is actually the constant pressure heat rejection, okay. So 1 to 2 is compression, where with the help of some compressor work input WC, you will be able to do this, W dot maybe, okay, or specific. Let us say if you had specific, then this heat rejection happens in QH or Q ejected, QR let us say here, okay. So that's Q ejected. Now 3 to 4 is not economical in a turbine. So clearly what you will do, instead of using a turbine, we will use expansion valve actually, okay, which is your throttling valve. You know, 3 to 4 is replaced with an expansion valve, is an expansion valve actually here, okay. In a throttling valve, you can say throttling, normally fluid expands during this, so throttling valve is what we are using here. Now in case of throttling valve, you can understand clearly throttling is highly irreversible. Throttling is irreversible process, one thing you know. And also throttling valve is actually very small, okay. If you see the dimension of the throttling valve is actually only for a small duration actually, okay. So during that throttling valve, what happens for the flow of this refrigerant through that small valve, what happens here is heat interaction in throttling, heat interaction Q to small throttling valves, because it won't get enough time for the heat exchange valves, is approximately 0, because Q is equal to Q dot into time, but clearly you can see this time over which the fluid stays in the valve will be very small, okay. So that's why this throttling won't have any heat interaction. That's why even in basic thermodynamics, in open system analysis, I think Shivam sir might have told you, in nozzles and basically in this kind of throttling valves, we don't take Q as, we don't consider Q actually, okay. So Q is taken as 0, because let's say for example if there is a pipeline like this, okay, and if you have a small throttling valve at this location, let's say if there is small throttling valve, then definitely what happens, by the time fluid crosses this throttling valve, the time it spends in the valve is actually very small, okay. So if you take this as the control volume, then to cross this small control volume from here to here, the time taken by the fluid is very small. Within that small time, there won't be any effective heat interaction taking place, okay. So Q is actually 0 in that case, okay. Now let's see, Q is actually very small. So if you see throttling, ds is equal to del Q by T plus delta S generation, okay. So let's say this is small q, maybe intensives we are writing, then this should be small q. Okay, if this is del q, then you know in case of throttling this is actually 0 and this quantity is always positive. So ds should be always positive in case of throttling. Okay, and we know irreversible process we denote with a dotted line. So therefore this starts here, and instead of having isentropic expansion, this fluid expands irreversibly to maybe some point here. This is 4. Okay, and this process should not be mentioned with a straight line. It is only and only with a dotted line. Okay, because this process is clearly irreversible. If process is irreversible and also it is not quasi-static clearly, so we don't know what are the intermediate states, we denote it with a dotted line. Okay, and once it reaches here, you can see this evaporator coils will take the heat again from the refrigerated space. So because of that heating, it again goes back to this particular state. So this is the cycle actually, 1 to 2, 2 to 3 and 3 to 4 actually. So this is the standard VCRS, vapor compression refrigeration system cycle, that we use in our refrigerators and all. Clear to all of you? Did you all understand how did we build this cycle? And if you draw the circuit for this, you can see you have a condenser and evaporator combination, and here you got a compressor. Of course, to compress this vapor, you got a compressor, and you got a expansion valve here. That's it. Okay, so you also got a expansion valve in this case. Okay, so this is the expansion valve, throttling valve. Now clearly this is evaporator, this is the compressor, this is the condenser, and clearly you can see so throttling is irreversible. So clearly this is the cycle, and if you put the numbers that I have kept on the top, this is 1, 2, 3 and 4. That's it. Okay, so this is how we have the cycle here. Got it? Okay, so this cycle corresponds to this particular TS diagram. Okay, now trying to analyze that this particular cycle. Now if you see practically, this cycle 3 to 4 is of course this equation, and throttling through small devices is also called isenthalpic process. You might have studied in this basic thermodynamics, because if you apply the steady flow energy equation, then clearly you'll find out delta H is equal to 0 in case of throttling process, because I'll just show you for throttling. Q minus W, or del Q minus del W, is equal to change in kinetic energies plus change in potential energies plus dH. If you see this, then clearly this is 0 and del W is also 0, because in actual case throttling valve cannot produce any effective work. So this is 0. And change in kinetic energy, let us suppose if you put the valve in a pipeline somewhere. Okay, so let's say if you keep the valve in some pipeline somewhere here, then before it comes to this point, means if you apply the control volume equation, at this point whatever is the average velocity, same will be the average velocity roughly. Okay, even though there is certain small change in temperatures and all, especially in case of gases, but normally in this particular part, it is, means during this part majority of the substance is in the liquid phase, because the Dynamis fraction along this curve is very small, along this particular process is very small. So clearly if you neglect this change in kinetic energies and of course no change in potential energy, this gives you dH is equal to 0, so H is equal to some constant. That's it. Okay, so that's why throttling to small devices is also called isenthalpic process, because enthalpy remains same. Okay, you cannot talk about temperature until and unless you specify ideal gas, some other assumptions, but as of now what you can say is only enthalpy is constant. Therefore throttling to small devices is isenthalpic, like these valves for example. Okay, so this is isenthalpic. Clear? So throttling is actually isenthalpic. So because of isenthalpic, this H3 and H4 at this location are same. Okay, so H3 and H4 is actually same at this point. H3 is same as H4. So in calculations, you need not again calculate H4 by calculating the Dynamis fraction here. Of course you cannot calculate the Dynamis fraction also. Maybe if something is given directly you can use, but you cannot calculate. So H3 can be taken as H4 always. Okay, now let us do certain mathematical analysis for calculating COP of this cycle. Okay, so COP analysis, let us see in this case. So firstly, you know, COP is equal to acquired desired effect. So here the desired effect is whatever the heat that is coming out here in this case QL, Q dot L, and let's say this is W dot C, capital W dot C, of course. Okay, then Q dot L divided by Q dot by W net actually, or W dot C, because anyhow this we have replaced it with throttling. In throttling you don't get any work output, so this can be written as Q dot H or Q dot L divided by Q dot H minus Q dot L, of course. Okay, because this is a refrigeration system at the out, so whatever the refrigeration system is taking out from the cold space and whatever it is rejecting to the atmosphere, so Q dot L and Q dot H is what you have here. Then let's see, W dot C is nothing but M dot times of H2 minus H1. Of course it's negative clearly, so this is negative, so minus of M dot C, M dot of refrigerant into H2 minus H1, correct? Because for compressor, you see, in case of compression, minus integral VdP, and we have seen normally in case of compressors this expression gives you the difference between enthalpies, because compression is isentropic, TDS is equal to dH minus VdP. So isentropic compression, this is 0, so dH and VdP are same actually, clear? So if you take VdP and if you integrate, you will finally end up with this difference, but this is specific for the total work interaction. Multiply this with the mass flow rate of the refrigerant. Clear to all of you? Okay, and this minus sign sustains as usual. Is this clear to all of you till this point? Yes or no? Please type in the chat box. Everyone, are you all understanding, or am I going too fast? It's fine. If you have any doubt, at least if one is having issue, please tell me, I'll slow down a bit. No issues. Okay, but please don't just go with the flow. Please try to understand each and everything. Okay, if you want me to repeat or if you want me to go slow, I'll do both. Okay, at any point. And I always tell you in my class, at any point, whatever might be the smallest doubt you have, you can always ask me. No issues. Okay, I'll never say I have both chota doubt hai, even you don't know this, nothing, I'll tell you. Okay, I'll explain you. Fine. So let's see. Anyway, this is the expression. Now clearly at constant pressure, so this is work input to the compressor. So Q dot L is M dot refrigerant into change in enthalpies, because it is phase change directly, H1 minus H4. H1 minus H4, and Q dot H is clearly M dot refrigerant times H3 minus or H2 minus H3. H2 minus H3. This is the magnitude. Okay, so these are the magnitudes, and these two are at constant pressures, and of course this is at constant temperature also. Now clearly you can see one thing. This guy Q dot L is called refrigerating effect. This is the main part of the story. Refrigerating effect. Okay, so this is called refrigerating effect actually here. So this is Q dot L, and this is mass flow rate of the refrigerant which is flowing in the circuit. So if you calculate COP is equal to Q dot L. So Q dot L, M dot refrigerant into H1 minus H4 divided by work input. So work input, if you normally in this expression, this is magnitude. So magnitude of work input to the compressor is, if you take magnitude, you have M dot refrigeration times H1 minus or H2 minus H1. H2 minus H1 actually here. Okay, so M dot refrigerant gets cancelled. So COP of refrigerant, COP of the cycle is equal to COP of VCRS is equal to H1 minus H4 divided by H2 minus H1. So you need not worry about H4, because this H4 can be made equal to H3. Okay, so this is H1 minus H3 divided by H2 minus H1, because why? You can see this 3 and 4 are same actually here. Okay, so this is what you have. So for throttling process में सबके सब 0 कैसे? Throttling में सबके सब 0 कैसे? Yeah, that's what I'm telling you. See, in this case, because of this understanding, there is no much heat interaction. That's why I made this 0. And potential energy changes nothing, because wall size is very small. So at the inlet and outlet, you can see, if you take the average elevation here from some ground reference, the average reference here is also same. Okay, and this do not produce any work to it. So these three terms are straight away zeros: del W, del Q, and del PE, and also DKE. Normally, if you are connecting, throttling valve is of very small size actually in general. So that's why if you see the average velocity of flow at these 2 points, you don't get much difference for this DKE. Okay, that's how this DKE is 0. Clear? Okay, so that's how we have H is equal to constant. So this is the expression for COP. Now you can also understand one thing here. refrigeration capacity is equal to m dot refrigeration into H1 minus H4. And what is mass flow rate of the refrigerant? You can denote this mass flow rate into the refrigerant as this conditions V1 dot divided by V1 actually, okay, because this is the volumetric flow rate, this is the specific volume. If you divide these two, you'll get mass flow rate into H1 minus H4. So if you understand one quantity, this is volumetric flow into the compressor, H1 minus H4 divided by V1, okay. So this quantity has certain importance. This quantity has got some importance here, yeah, this quantity, which is called volumetric refrigeration capacity of the plant. Volumetric refrigeration capacity means for 1 unit flow of refrigerant, for 1 meter cube per second flow of refrigerant, what is the cooling effect that you get? That's it, okay. So volumetric refrigeration capacity, okay. So this talks about the size of the plant. Let's say for example, if demand is 10 tons of refrigeration, and for 1 meter cube per second, if you have this much amount of refrigeration, then you can decide what should be the flow of refrigerant, V1 dot, okay. If flow is high, then definitely devices has to be bigger. So this volumetric refrigeration capacity decides the size of the devices in the plant, okay. So this is the calculation. Then COP is done, okay. Now what are the observations that you can make because of converting this to reversed Rankine cycle? Actually, if it's a Carnot cycle, it would have got maximum COP, but clearly COP will decrease now as compared to the Carnot cycle. I can easily show you COP decreases because we need two things for understanding it. Look, I'll draw the Carnot cycle and this VCRS on the same diagram. You will observe. So TS, let's say you have constant constant pressure, which is P evaporator, okay. So P evaporator, and you also have P condenser. Okay, and this is P intermediate somewhere. So this is P intermediate, okay. Now let's say first I'll draw the VCRS. Oh, I think it's going very long. So this is P condenser and this is P intermediate, maybe somewhere, okay. So that you have the VCRS like this. Okay, so this is the situation, and clearly this is your TL, and this is your TH. Normally, of course, in case of Carnot, this is TH, but normally you have some mean temperature of heat addition. Okay, if you if you draw a Carnot within the same domain, let's see what would have happened. You would have got something like this. Then this P intermediate should pass like this. Just a minute. Yeah. This is your P condenser. This is your P evaporator, and clearly this is your P intermediate. Okay, now you got this. And in case of Carnot cycle, your expansion would have been something like this. Your expansion would have been something like this actually, and this heat rejection would have been this. Okay, or heat addition into the cycle could have been this. So if I name this cycle 1, 2, 3 and 4. So 1, 2, 3, 4 is your VCRS, standard VCRS, of course, standard VCRS. Okay, compression work increases. Of course, compression work increases, but there are a few more things which you can identify actually here. C. One, two, three, four is standard VCRS. Now let's see 1, 2 dash, 3, 4 dash. So 1, 2 dash, 3, 4 dash, 1. Okay, so 1 is your Carnot cycle, reversed Carnot. You can say reversed Carnot, reversed Carnot. So this is your reversed Carnot. Okay, so this, and this. Fine. Now clearly one thing you can understand, if you calculate thermal efficiency on the basis of course I'll also tell you refrigeration effects, but if you normally see, this is 1 minus TL by TM actually, okay, or TH, let us say. This is COP, sorry, I'm writing efficiency. COP is TL by TH minus TL, which you can also write as 1 by TH by TL minus 1. This is the effect, expression for COP. Okay, in case of Carnot cycle, COP of Carnot. COP of Carnot. Okay, now this is what you know, but now you can understand in both the cycles, at all these points, heat addition happens at basically this TL is same in both the cases. Okay, if you take the interpretation, since temperature is constant all over, maybe for 4 to 1 or 4 dash to 1 doesn't matter, TL is same, means in both the cycles this TL will not change. As or no, TL remains same. This TL remains same even for standard VCRs. But if you see the TH, this TH is here, this TH is actually here at all these points for Carnot cycle, but in case of standard VCRs, some part of heat is getting rejected at a higher temperature. If this is increasing, can anyone tell me, if I define something called TH mean and TH, can you tell me out of between these two what is the symbol I should put? Look, TH is actually this temperature and TH mean is the mean temperature of heat ejection in the process 2 to 3. So can anyone tell me out of these two, between these two, which symbol should come? Greater than, less than, equal to something? Come on, please type in the chat box. Come on guys, quicker. Equal, greater, less than, equal and greater is typed already, so less than is pending. One of you please write less than in the chat box. It's get. Yeah, mean will be greater actually. Okay, so TH mean is greater because clearly at all these points, right from 2 to let's say for example, if I call this point A, 2 to A, this part of heat ejection is happening at a higher temperature, okay, as compared to this part, and this part is same. A to 3 is same in both the cycles. So in standard VCRs, 2 to A is happening at higher temperature, so clearly the mean temperature of heat ejection, which is TH, actually increases. Okay, so if TH mean increases, means let's say if this quantity is increasing, then definitely this total ratio will increase because TL is fixed. So if numerator increases, this total value increases. If this total value increases, then this 1 by the total value decreases. So COP will decrease, and therefore COP of standard VCRs, COP and standard VCRs will be less than COP of Carnot, which we already know from our second law analysis. Of course, this is also second law analysis, but second law tells you that between same temperature limits and of course isothermal heat additions and rejections will have better performance for the cycles. Okay, so this you can also show from this TH mean actually. Also, you can understand this this COP will decrease from two other points. Look, let us say if you have TS, TS, and you got the dome like this. If you draw a Carnot cycle, for example, okay, so this is the Carnot cycle. 1, 2 dash, 3 and 4 dash. Okay, and the pressures in this is P evaporator, P intermediate, and let's say you also got P condenser. P condenser actually. Okay, so this is P evaporator and P condenser. Now, if you plot this standard VCRS, see how it turns out. Okay, now 1 to 2, clearly 2 to this point, which is 3, and 3 to 4 is something like this, and 4 to 1, which is again this line, along this line. Okay, and this is the cycle. Now clearly, 1 2 3 4 1 is standard VCRS. Standard VCRS 1 2 dash 3 4 dash 1 is Carnot, reversed Carnot. Reversed Carnot actually here. Okay, so this is the reversed Carnot. Now let's see, in this case of reversed Carnot, this part of heat addition or heat which is added in the cycle is unnecessarily added. Okay, so this part is called superheated horn. Is called the superheated horn. Okay, superheated horn. And you have certain compressor work input WC, and also you have seen one thing. If the cycle is actually Carnot cycle, I mean reversed Carnot cycle instead of standard VCRS, you have refrigeration effect. Refrigeration effect in case of Carnot, reversed Carnot, in case of reversed Carnot could have been H1 minus H4, correct? So this would have been H1 minus H4, but because of this conversion, refrigeration effect in case of standard VCRS, if you take the standard VCRS, so what's going to be the value? Actually it is H1 minus H4, that's it. H1 minus H4, this is dash, H4 dash, H4 dash. Okay, now clearly you can understand one thing from this diagram. H1 minus H4 will be less as compared to H1 minus H4 dash. Yes or no? Because 4 dash is still to the left of 4. So clearly from your basic properties of your substances, calculation of enthalpies in the wet region, all these things, you can clearly understand this difference in enthalpy will be definitely less as compared to this difference in enthalpy. So by converting the reversed Carnot to standard VCRS, what's happening? Your refrigeration effect is getting reduced. Okay, so if you observe COP is equal to Q dot L by W dot in. Okay, so this is what you have. Clearly this refrigeration effect is dropping. This means by converting this reversed Carnot to standard VCRS, this Q dot L is actually dropping. Okay, so this Q dot L is actually coming down. And also you can see, if the cycle is only Carnot cycle, reversed Carnot cycle, from this point to this point, the compression is only from P evaporator to P intermediate. But now because of converting to standard VCRS, it should be compressed from P evaporator to P condenser directly. So this compression is of higher duration now. Okay, so which means compressor load will increase, because if you see WCV minus integral VdP, this pressure change dP is not the equal in both the cases. In first case, in case of reversed Carnot, it is only from 1 to 2 dash, but now it is from 1 to 2 actually. So pressure difference is increasing. So definitely load on the compressor will also increase because of this. So load on the compressor is increasing clearly. This quantity is increasing, so COP will fall definitely. Okay, from the points of understanding of temperatures in case of this TH mean, and also from this understanding of this ratios Q dot L by W dot in both these cases you can understand COP will actually reduce. So that's why this cycle has still some chance for improvement actually. Is this clear to all of you? Yes or no? And because of this conversion, the system actually suffers some loss, which is this 4 dash. This point is 4 dash. This amount of heat, because del Q is equal to area under the TDS diagram, so this amount of heat is not ejected from the refrigerated space. Okay, and this energy loss, which is loss in refrigerating effect, so this area corresponds to loss in refrigeration effect, and this loss is because of throttling. If you have not throttled the substance, if you have used some isentropic expansion, you would have got H1 minus H4 refrigeration effect, but because of throttling you are losing this amount of heat taking out from the refrigerated space. So this is also called throttling loss, and this is called the superheated horn. Okay, so these two areas play a very important role. Loss in refrigeration effect, yeah, of course. Okay, because of this throttling, we'll have certain loss in the refrigeration effect, so that's also called throttling loss. And these two areas, this, if you call normally this area as A1, and if this area if you call A2, this A1 and A2 decides how closely you can bring the system to Carnot cycle. Okay, let's say if this A2 is coming very small and A1 is also coming very small. Okay, let's suppose instead of this point here, if I end up here, throttling loss will reduce. Okay, so these two play as important parameters when you're talking about COPs. Got it? Okay, and depending on A1, A2 values, we decide how much close is our cycle to the actual reversed Carnot cycle. Got it? Yes or no? So please type in the chat box. Okay, yeah, got it, right? Now let's see one more thing which is effective in this case is, since the COP formula is very much significant on enthalpies, we'll sometimes feel easy to denote this cycle on a pH diagram actually. Okay, so H3 is equal to H4 dash also? No, because see, this process is not isenthalpic. Now 3 to 4 is not isenthalpic, it is isentropic. Means if you see TDS is equal to DH minus VDP, then clearly you can understand one thing, this DS is not equal to 0 now. Okay, because DS is equal to 0 of course, so DH is equal to VDP and this VDP is not equal to 0. Okay, so this is 0 for 3 to 4 in case of Carnot. Okay, not in 3 to 4 dash. This equation, this is isentropic expansion, so DS is 0, but DH is not equal to 0 because VDP is not equal to 0 here. Okay, that's why. Now let us see the pH diagram, because since you have seen the expression of COP in terms of COP is equal to H, what is the way we have written, H1 minus H4 divided by H2 minus H1, which is same as H1 minus H3 divided by H2 minus H1. Okay, frankly speaking guys, if you open PYQ book, if you know that formula, half of your refrigeration questions will be done. Okay, because in GATE actually if you see questions, many questions turns out on this formula, that's it. Okay, but of course if you go to ESC, all the auxiliary devices, valves, everything we have to study, but right now in GATE at this level only this is fine. Clear? Actually if you see refrigeration and air conditioning is one separate subject in case of ESC syllabus. Okay, you might have seen. Did anyone of you see ESC syllabus? Engineering services syllabus of mechanical? Have you seen? You have seen, right? Yeah. Basically if you open ESC syllabus, then definitely you'll see refrigeration and air conditioning is one separate subject again there. Okay, so we have to go in much detail with all the devices. Okay, what happened to the curves, each and every point, but as far as GATE is concerned, you just have to know these cycles a bit. Okay, that's what. Clear? So in pH diagram, how we denote is pH, and the shape of the dome will be something like this here. Okay, like in your Wallah chart you might have seen. Of course Wallah chart is between enthalpy and specific enthalpy, but the curve looks something similar. Okay, now you have two pressures between which you are operating. So one is P condenser. So this is P condenser and this is P evaporator. Okay, so I have solved PYQ simultaneously with your this course. Are you all getting answers or not? Okay, I wish you'll get, and I hope you are getting. Fine. So let's see. So first, process 1 to process 2. So clearly you can see in this process of 1 to 2, you'll actually have pressure rise, and if pressure is rising at this dry state, definitely whatever is the work you're adding, that increases to the enthalpy. Means if you see H2 is equal to H1 plus work input into the compressor specific. Okay, because simple energy balance, you can see if you apply first law, then you can get this. H2 is equal to H1 plus WC. Okay, now let's see this 1 to 2. So pressure increases, enthalpy also increases clearly. So the graph comes something like this, 1 to 2, both increase 1 to 2. And guys, one thing I am telling you, the shape of this line and the shape of this dome depends from efficient to efficient actually. Okay, I'm just giving you some basic idea that 1 to 2 it increases. Clear? So this is how the graph. Then at constant pressure you are doing this heat rejection 2 to 3. This point is 3. Now 3 to 4 it's isenthalpic. So let's say 3 to 4 is isenthalpic. So this will be a isenthalpic. We don't know what's happening in between, but the state 3 and state 4 will have same enthalpy. And 4 to 1 is what you have here. Okay, 4 to 1. This is the case. So 1, 2, 3, 4 is the cycle actually. So here in this case you have the work input in the compressor, and this guy is the heat rejection, and this is the heat addition QS, let us say in this case, and of course small amount of nothing comes out here, just the isenthalpic process. So therefore H1, H2 and H3. H2 will be generally given for you. H2 is given because that's the superheated condition. So H2 is given actually, otherwise they have to give you CP and temperature difference, you can calculate. Okay, but generally they'll directly give this H2. Now H3 is nothing but H3 is HF at P condenser, and H4 is same as H3, and H1 is normally HZ at P evaporator. So sometimes what they give you guys, sometimes what they do, instead of giving this point 1 here, they'll give you somewhere here. Okay, then at that time they'll give you Dyna's fraction and you have to calculate H1, like the calculation of questions we done in a Rankine cycle. Okay, so if they give you this point somewhere here, 1 to 2 difference between H2 and H1 is nothing but your compressor work. So 1, instead of giving directly, if they want you to do some calculation, they'll give you some point here and they'll give you Dyna's fraction. Okay, so you can calculate what is enthalpy at state 1. That's how you're going to do this. Okay, so is it clear to all of you? It's already 5 o'clock, 1 hour for VCRs. Fine. Okay, so is this clear to all of you? So please type in the chat box. Yes. Okay. Yeah. Now normally this P condenser, normally the refrigerators and all coils, if you see, they reject heat to the atmosphere. Okay, you might have seen, normally if you see the condenser coils at the back of your fridge, they actually give heat. Did anyone of you touch the back side of your fridge anytime? Let's say if you have a refrigerator, I'll try to draw the box, some of you can see. Fridge will be like this, no? Normally. I'm very bad at this, guys, but please, try to understand some things at least. Okay, this is the front face and back face, of course. Here you have your electric motor, you might have seen. This is motor. Normally this will be connected to some power supply. Okay, so this will be connected to some power supply. Normally you see, always the wire for your fridge comes from somewhere here. At your home, if you have a fridge, you can see. Sorry, didn't get yes. Call get hot, didn't get you. In older fridge, it is behind. Yes, of course. Nowadays they are putting it wherever they want, but normally if you see the fridges of normal household, you will have this motor here. Okay, so from here one wire comes out and you will put it into the plug. Okay, and this motor in turn drives the compressor, and here you have some coils. What are they? These coils are called evaporator coils. Evaporator coils actually. Okay, so they are called evaporator coils, and these evaporator coils are connected to this compressor. And you can see at the back of the fridge you have this black, normally if you see, generally you can find this on the back door, on the back of the fridge you can see we have this. They are called the condenser coils. Normally you can see all these things if you go to a service shop. Condenser coils. Okay, they have seen this condenser coils actually, and you will have a small expansion valve here. So small expansion valve is there. You can see small expansion valve will be there here, so that this circuit continues all over. Okay, so but anyway, if you go to any refrigerator repair shop or service station, you can, when they open it, you can see this. Sorry, coils get cold or hot. Coils which are in contact with the evaporator, they generally get cold. Okay, but coils which are here, they get hotter. Even you can see, if you go at the back of your fridge and if you touch, of course you cannot see coils practically because there is some nice insulation and some nice design is there. If you open the fridge, don't open, okay, but if you open, then what happens, you can see coils will be there. Even though without seeing coils, you can see whenever you put your hand at the back of your fridge, you will feel some hotness. Okay, that hotness is because this condenser coils will actually eject heat to the atmosphere. Okay, so this condenser coils, normally this P condenser will be the atmosphere, I mean P condenser is there, but TH will be normally the atmospheric conditions. Okay, because heat rejection happens to the atmosphere. Okay, now let's see. So anyway, so yeah, this is the story, and 1, 2, 3, 4, this is how we get the gas. Now if you want to increase COP, what you can do is, generally P condenser, the heat rejection is to the atmosphere, so that is locked in general. So how efficient temperature is maintained low throughout here? Yes, good question. How efficient temperature is maintained low? That's the question. Is maintained low? Yes, nice question. ओके सर HPCL के पेपर में नॉन टेक को आया इतने बड़ा मार्जिन में, हाँ आता है ना 85 मार्क्स, पहले जब नोटिफिकेशन रिलीज किया उस टाइम पे ही उन लोगों ने बोला था. फाइन. So what we are talking, how this question, so basically why or how efficient temperature is maintained low, that's the next question. Okay, because you can see in this part 2 to 3, because it's generally hot, you know, it's fine, but how the efficient temperature is maintained at this low temperature, that's the question, right? Now how this TL is obtained, you all might have heard about something which is called Joule-Thomson coefficient. In your basic thermodynamics, I think you might have heard. If not, you can hear here, it's fine. Joule-Thomson coefficient, which is called 𝜇𝐺T. Actually, have you heard this? Did you all hear about this Joule-Thomson coefficient? Okay, Joule-Thomson coefficient. Have you all seen this Joule-Thomson coefficient? Yes or no? Okay, yes. Now basically for any efficient 𝜇𝐺T has to be positive or negative? Has to be positive or negative? What should be the Joule-Thomson coefficient? If you want to work out a substance as efficient, what should be the Joule-Thomson coefficient of that substance? It is kept inside inverse curve, positive. What is inverse curve? What is inverse curve? Fine. Let's see. This is positive, of course. Okay. If you see this Joule-Thomson coefficient, 𝜇𝐺T, if I want to just explain you, 𝜇𝐺T actually. So this 𝜇𝐺T is nothing but dou T by dou P in a isenthalpic process actually. Okay, in a isenthalpic process. Now if you see this cycle, for example, if you see this cycle during throttling, this is the isenthalpic process 3 to 4. During throttling, what we are doing actually, we are decreasing the pressure. Okay, so during throttling, dP is negative, correct? Because initially the fluid is at higher pressure, you are making it fall to lower pressure because of this expansion. Okay, we have some expansion valve, we are expanding. Now if this substance has to work as efficient, means by the time it reaches this coils, or maybe it reaches this evaporator, if the temperature has to be very low, then definitely what happens, by the time this pressure falls from P3 to P4, which is nothing but P condenser to P evaporator, your temperature should also fall from TH to TL. Yes or no? That means for the substance to be efficient, for the substance to be a refrigerant, for the substance to be efficient, dT should also fall along with pressure. Okay, otherwise, let's say if it is happening in the other case 3 to 4, definitely by the time it's falling from 3 to 4, pressure is falling, but let's say if temperature is increasing, then what happens, actually instead of flowing this cold fluid here, you will actually flow the hot fluid in this evaporator coils, then definitely your fridge works as a heater. Whatever you put inside, they get heated up instead of getting cooled. Okay, so that should not happen. So therefore this substance, whichever is undergoing throttled, that during pressure drop, it should also undergo temperature drop. If this is negative and if this is also negative, negative by negative gives you positive for refrigerant. That's how you get this. Okay, so dt by dp, and clearly you can see mu jt. If you want to generate an expression for mu jt, we all know change in enthalpy is equal to Cp dt plus V minus T into dou V by dou T at constant pressure into dp. You know this, correct? So this is what you all know. Normally in your basic thermodynamics, in thermodynamic relations, you might have seen this. Now, for isenthalpic process, dH is 0. For isenthalpic process, okay? So this gives you Cp dt plus V minus T times of dou V by dou T at constant pressure times dp is equal to 0. Okay, now you can understand, if you want dt by dp at constant enthalpy, okay, so at constant enthalpy actually, so dt by dp at constant enthalpy, this gives you 1 by cp times of T times dou V by dou T at constant pressure minus specific volume. So this is the expression for calculate, and this is your Joule-Thomson coefficient, mu jt actually here. So this is your expression for Joule-Thomson coefficient. Okay, now normally you all know during throttling of ideal gas, what happens to temperature? You know, dH is equal to 0. So if you write Cp dt is equal to 0, then definitely Cp is not 0, definitely. So dt has to be 0 in case of ideal gas. Okay, so throttling of ideal gas. Throttling of ideal gas actually. Of course, perfect gas you can say, maybe perfect gas anyway, because again in some books you find this perfect gas. So throttling of perfect gas, then dt is actually 0, which you know, because if in isenthalpic, if dH is 0, dH is nothing but Cp dt, so Cp is not 0, so dt has to be 0. So inlet temperature of the gas should be same as the outlet temperature of the gas. If temperature difference is 0, but throttling clearly decreases your pressure, for ideal gas, during throttling, dp is negative, definitely pressure falls. But what happens to dt? This is 0. So definitely what happens to your mu jt? This also should be 0, because dou T by dou P has to be 0 clearly. Yeah, that's why ideal gas we cannot use as refrigerant actually. Clear? In this cycle. Okay, because if you are doing throttling, okay, if you are using throttling here, then definitely you cannot use ideal gas as a refrigerant, because if this is 0, that means this, by the time ideal gas falls from P3 to P4, but temperature remains as TH, then definitely what happens? Heat will flow in the reverse direction to the cooled space. Okay, then your cooled space get hotter. It's no more a fizz, it's something else, it's a heater. Understood? Clear? And also you have understood this. Also you can see from this expression, you can get this. Okay, because if you calculate this value for ideal gas, considering T into dou V by dou T at constant pressure minus P is equal to, in ideal gas PV is equal to RT, so V is equal to RT by P is what we have here. Okay, so if you differentiate this, T into dou V by dou T at constant pressure. Okay, so if you differentiate this with respect to constant pressure, we have R by P minus, this is V, sorry, this is V minus V. RT by P is nothing but V, so this gives you 0. So if this bracket is 0 divided with Cp is also 0. Okay, that's how. Clear? So that's why you should not use ideal gas as a refrigerant. If you use ideal gas, your fizz stops working. Normally in our cases ammonia or nowadays chlorofluorocarbons are also being used. So all these things are refrigerants actually. Clear? Now someone is talking about something, what I forgot, inversion curve. Okay, so what is this inversion curve? Normally if you see, oh sorry, I think I have added this inversion curve. Inversion curve. To understand this inversion curve, if you see temperature versus pressure, on temperature versus pressure axis, if you draw enthalpy curves, constant enthalpy curves, it comes out something like this. So this is H1 is equal to constant, H2 is equal to constant, H3 is equal to constant. These are lines of constant enthalpies. Okay. So sorry, nice. Okay, fine. Naam thoda bada gaya. Okay, fine. See, this is H1, H2 and H3. Okay, so this is what you have. And actually guys, this is GATE 2022 question. 2022 or 2021, I don't remember. I think 2021. GATE 2021 question. Okay. The Joule-Thomson coefficient of ideal gas is dash 0, positive, negative. I think some other option is given, but this is the simplest way you can show that mu Zt, Joule-Thomson coefficient of ideal gas is actually 0. Okay. But anyway, all this stuff might have taught you in Sir might have taught you in basic thermodynamics, just because since you asked this question, how efficient temperature is maintained low, because we'll choose a efficient which is having less a positive Joule-Thomson coefficient. That's it. Okay. Now let's see if this is the case. At this point you can see all these are constant enthalpy processes. If you construct a curve like this, you will eventually be able to make a curve like this. Okay, so you can make a curve. This curve is called inversion curve. Now why this is called inversion curve? The reason is, if you calculate slope here at this point, okay, of course if this is a temperature versus pressure graph, dt by dp is nothing but slope of curve on TP diagram. Slope of isenthalpic process on temperature versus pressure diagram actually. Okay, so this is temperature versus pressure diagram. Now clearly you can understand, if you take a tangent here, look, if I draw a tangent here, this tangent will definitely make an angle less than 90 or more than 90. Come on, tell me. And this is nothing but tan theta, where theta is, in basic calculus, I think I might have told you many times, or maybe Rahul sir might have told you. So theta is angle made by tangent with x-axis with pressure axis, of course here, in anti-clock direction. You know this, right? Okay, so in anti-clock direction. So tell me, if I draw a tangent here with pressure axis, by the time it meets pressure axis, the angle made by the tangent will be more than 90 or less than 90? Quick. If you draw a tangent here, the angle will be more than 90 or less than 90? Means if you extend it, slope of the tangent, if this is your pressure axis, if you extend it, then you can see this angle, not 180 completely, but you got some angle. So let's say this is the curve extension. So this angle is more than 90, correct? It is greater than 90 degrees. So if this is greater than 90, then slope is negative actually. Okay, tan theta. So theta is more than 90, tan theta is negative. So clearly this has a negative slope, which means in this complete region, mu Jt is negative. And here if you take tangent, clearly this will make an angle which is less than 90. So clearly inside this curve, mu Jt is positive, and exactly on this line, because this is the line which acts as transition from negative to positive. So this line is called mu Jt is equal to 0 at this point, and this is called inversion curve, because this curve decides the nature of the substance. So something beyond this, if you cross this curve, definitely the nature of the fluid gets inverted. Okay, means the substance which is not acting as efficient till this location, it starts acting as efficient as soon as you cross this curve to the left. Okay, and all your efficients like ammonia, all these things, chlorofluorocarbons, whatever, all this lie within this particular region actually, and this temperature is called maximum inversion temperature. So this is called maximum inversion temperature, and if your temperature of TH is more than maximum temperature, you cannot use that diagram. Okay, you cannot use that efficient in your cycle. Okay, let's say for example, if I take ammonia, as efficient, and let's say for ammonia there is some Tmax. Okay, so this is the inversion temperature. If your TH in the efficient cycle is more than this TH, then definitely you will enter a zone where mu Jt is less than 0. So ammonia won't work for your cycle, even though ammonia is normally efficient, but that won't work for your cycle. Understood? So that's why mu Jt plays a very important role in selecting the efficients. Clear? Curve about which values of Joule-Thomson coefficient changes. Yes, that's called the inversion curve. Okay, from positive to negative. Nature of the fluid gets inverted about that curve. Okay, so that's called the inversion curve. Did you all understand the importance of this? Okay, clear? Yes or no? Come on guys, type in the chat box. Did you all understand how we'll actually maintain the low temperatures of the refrigerant all over? Okay, fine. So one more thing I just want to tell you before I go for this vapor absorption systems, refrigeration systems. You can see nomenclature of refrigerants. This is a bit important. Sometimes in all your ISR also they can ask you this. Nomenclature of refrigerants means how you decide the chemical formulas and names for them. Refrigerant. Okay. Nomenclature of refrigerants. Guys, one thing I'm just skipping here because it's generally calculated. Let's say they'll ask you if condenser pressure is kept constant and evaporator pressure is increased, what happens to COP? All these things they ask you. Just a bit of mathematical analysis, just understanding one fraction could give you the answers. Okay, like let's say for example here at this point, if I say normally if you have a standard VCRs, okay, so you have standard VCRs like this. If I say keeping condenser pressure constant because normally it's atmospheric, but if you increase this peak evaporator, what happens is what they'll ask you. Okay, if you increase this evaporator, then definitely what happens, TL mean temperature of heat addition increases, but this remains constant. So depending on that you can calculate whether COP increases or decreases, all these basic things. Okay, so please do that by yourself. Again, it's easy. So nomenclature of refrigerants, this is a bit important. Normally refrigerants, if you see, refrigerants, if you see, you have two guys, which is organic like chlorofluorocarbons, all these things, and inorganic refrigerants. Now the nomenclature here is RXYZ and here it is R7XY. So you can see this is a bit easy, inorganic, to identify. This XY is nothing but molecular weight of the refrigerant. Molecular weight of refrigerant. Molecular weight of refrigerant. For example, if you take ammonia, NH3, you know this has got a molecular weight of 17. Okay, because nitrogen is 14, 2 times of 7, and hydrogen is 3 hydrogens. So 14 plus 3 is 17. So normally this ammonia, which is used as refrigerant, is normally denoted as R717. Okay, so if someplace if you see R717, this is nothing but this first letter of 7 after R denotes it's a inorganic refrigerant, and 17 molecular weight corresponds to ammonia. So that's how it is ammonia. That's how you identify. This is the symbol for ammonia. Okay, now coming to this, guys, this is a bit interesting to look at. RXYZ. So if you see in this, X is number of carbon atoms minus 1. Y is actually number of hydrogen atoms plus 1, and Z is number of fluorine atoms. Number of fluorine atoms, actually. Number of fluorine atoms. This is how we denote the 717 refrigerant basically is ammonia. Now number of fluorine atoms is this. Now try to understand one thing. Normally if you take carbon, a full alkane, you all might have studied these things in your saturated hydrocarbon. In your plus 11 or plus 12 you might have studied this carbon valency is 4, all this stuff actually. Okay, now let's see, if you have n carbon atoms, if all the bonds are saturated, means single bonds, you have 2n plus 2 hydrogen atoms which can be attached to that. Okay, and in case of unsaturated bonds, like in case of alkenes and alkynes, you can see you don't have this 2n plus 2, normally have 2n minus 2, all these things. Now if you see, X is equal to number of carbon atoms minus 1. Okay, so you have number of carbon atoms minus 1. So basically in a refrigerant, number of carbon atoms is equal to X plus 1. Correct? Yes or no? Because if you shift this minus 1 to the left hand side, you get X plus 1. So in a refrigerant, you have X plus 1 carbon atoms actually. If you have X plus 1 carbon atoms, how many bonds can be formed? 2x plus 2. So 2 times of X plus 1 plus 2. These many bonds can be formed. Okay, so total number of bonds total number of bonds is formed is basically 2 times of x plus 1 plus 2 can be formed. But out of this 2 x plus 1 plus 2 bonds, number of hydrogen atoms, if y is number of hydrogen atoms plus 1, number of hydrogen atoms is equal to y minus 1. Okay, so 2 times of x plus 1 plus 2 minus y minus 1, because this y minus 1 corresponds to number of hydrogen atoms, plus z. Let's say if there is some difference for this, okay, then definitely this difference is nothing but number of chlorine atoms. Chlorine atoms. Understood how we are doing this? So this is the total available bonds for the carbons, for n carbons. Now out of this n remaining bonds, if you have y minus 1 plus z combination, then definitely that's nothing but your chlorine atoms. Like for example, I'll just tell you about one refrigerant R12. And guys, look, normally you should have 3 numbers. This is not 7, so clearly it's organic. But in case of organic, you should have 3 carbons actually. But you're having only, you should have 3 numbers x, y, z, but you have only 2 numbers. That means this is 0, 1, 2. Okay, so normally 12 can be written as 0, 1, 2. You understand? Yeah, this one, this equation, right? Okay, I'll work out this example so that you will get clarity. Okay, example, look here. Let's say if you have only 2 digits after R, that means it's an organic refrigerant. The third digit you will put as 0. Now let's see if I compare this with my formula, of this, with these formulas. X is equal to 0, x is equal to 0, y is equal to 1, z is equal to 2. Okay, so this is what you have seen. So if you see number of carbon atoms is equal to x plus 1, so which is 0 plus 1, so there is 1 carbon atom. Okay, so this is 1 carbon atom. Now let's see number of hydrogen atoms. Y minus 1, so y value is 1, 1 minus 1, 0 actually. Okay, so this is 0. Number of fluorine atoms is equal to z, so which is 2 actually here. Okay, so as of now if you see the formula, we have 1 carbon atom, no hydrogens, there is no hydrogen atom, there are 2 fluorine atoms, so CF2 is what we have. But what is the valency of carbon? Carbon should have 4 bonds. Okay, let us suppose if you put x equal to 1 here, then 2 times of 2, 4 plus 2. Okay, so I think 2x plus 2 na? This is carbon atoms, no? This is the total number of carbon atoms. So if you have only 1 carbon atom, so if you put this x plus 1 is equal to 1, you can see this x plus 1 is equal to 1. So if you put this x plus 1 is equal to 1, this 2 into 1, 2 plus 2. So total you should have 4 bonds. Okay, but hydrogen atoms is 0, fluorine atoms is 2. So this y minus 1 is 0 and z is actually 2. So if you put this x plus 1 is equal to 1, 2 into 1, 2 plus 2. This is total 4. 4 minus 0 plus 2. So this is only 2. So 4 minus 2 is actually 2. So we have 2 chlorine atoms in this. So this is called CF2Cl2, which is very dangerous chlorofluorocarbons. Chlorofluorocarbons. CFCs, highly dangerous for ozone layer. Okay, so these are CFCs. Got it? Did you understand? Now did you understand how I made this calculation? Normally if there are n carbon atoms, it should have 2n plus 2 bonds in the saturated state. Okay, so therefore if there is x plus 1 carbon atoms, because you see number of carbon atoms is x plus 1, so if you have x plus 1 carbon atoms, so 2 times of x plus 1 plus 2 is the total number of bonds that should be there. But so if there are these many bonds, then there should be those many elements connected to carbons. Okay, so these are the summation of hydrogen plus fluorine atoms. So any difference between these two should be the balanced carbon, this chlorine atoms. Okay, so that's how we calculate chemical formula. If they give you R012, they'll ask you R12 has a chemical formula of, they'll give you options: CFCl2, CF2Cl2, CFCl3, something like this. So the correct option is CF2Cl2 actually. So this is how you write chemical formulas from this numbers notation. How we came to know that it's remaining chlorine only? Because if it's intentionally we make chlorines. Okay, that's why. Clear? Why fluorines and chlorines are used, we will come to know maybe after some time. Of course, we are not going into detailed discussion, but there is some technique called in this refrigeration. We have another technique which is called VARS, vapor absorption refrigeration systems. They will see. Okay, normally this halogens, fluorine, chlorine, bromine, all these things are very powerful refrigerants. Okay. This is how we have CF2Cl2. Clear? So normally sometimes they give you this. By performing these simple calculations, you should be able to write chemical formulas. Okay? Or if chemical formula is given, you can go in a reverse order. You will be ending up with this calculation of R12. Understood? So this is how the story of organic refrigerants is done, and inorganic directly you can do this. Okay? Why I'm putting this much stress on VCRS is normally questions, majority of the questions comes from VCRS. Okay? If you open your PYQ book, you can find easily 95 to 97% of questions from refrigeration in GATE. Okay? In GATE comes from VCRS. If you can open normally your books, you can find out. Okay? Did anyone solve all the PYQs of refrigeration previously before attending these classes? If not, you can definitely solve now. You start attempting, you can solve easily. But if some of you have done already, you can see majority of the questions are from this VCRS. All the questions, 98, 90, only 2-3 questions are from this gas power cycles. That too based on simple knowledge of this COP is equal to 1 by thermal efficiency, all this stuff. Okay. Now anyway, let's go to the next technique. Okay, still we have to start gas also. What is the time by the way? Oh, 5:30. Let's see. Fine. So second is vapor absorption refrigeration technique. Vapor absorption refrigeration technique. Refrigeration VARS system. Okay, of course, I won't draw all this diagram. This is just for your knowledge. Okay, VARS, vapor absorption refrigeration system actually. So the main difference is, if you take this loop, this one which I initially told you, here this evaporator condenser pressure, decreasing mechanism, which is a valve, all these things are same, but this pressure increasing mechanism is very easy. Okay, very simple. Now how we are going to do that? See, your main aim is to take the refrigerant which is at low pressure to high pressure, correct? That's what you have to do. Now normally you are doing it in gaseous state, so that you need a compressor, and you are normally putting so much compressor work. By somehow, if I can convert this vapor refrigerant to liquid, and if I want to convert liquid from low pressure, if I want to transfer liquid from low pressure to high pressure, I need a pump, and comparatively pump work is very less as compared to compressor work. That's how actually for the same amount of refrigeration effect, I will actually save my compressor work, so that you can do the refrigeration very easily. Okay, see how it is done. You again have an evaporator. You again have a evaporator and also condenser. And you also have an expansion valve. You have an expansion valve like this. Okay, so this is your expansion valve actually. Okay, so this is your expansion valve. This part is same till here. Okay, so this part is the same actually. Now the only thing that changes is this configuration. See what happens here. Before going for this cycle directly, I want to explain you some bit of chemistry today. Absorbent. This word is important. Okay, basically from your schooling, absorbent, the thing which absorbs some other thing, is called absorbent actually. Okay, now if you see certain combinations, H2SO4 plus water, this H2SO4 is having high affinity for water. Affinity is ability to attract actually. So this is absorbent in this case. Okay, so absorbent. Clearly this is H2SO4 plus H2O. Normally if you take H2SO4, this H2SO4 is having high chemical affinity to attract water molecules. Okay, so H2SO4 plus H2O actually, it is absorbent. Similarly, if you have other combinations, ammonia or water plus ammonia, water plus ammonia, this water is the absorbent in this. Water absorbs ammonia easily. Okay, and similarly you have other combinations like lithium bromide and ammonia, where lithium bromide is the absorbent, all these things. But anyway, just the main idea is if you bring one fluid near to other which is having affinity, means let's say if I have some H2SO4 and if some water is spilling over here, if I try to bring that H2SO4 very in contact to that water, then definitely what happens, this H2SO4 will try to absorb all this water. That's what. Okay, did you all understand this? Yes or no? Please type in the chat box. Yes or no? Did you all understand this chemical affinity? Chemical affinity between two substances, which means if you bring these two in contact, this H2SO4 will actually take in this water. It will try to absorb all the water. That's what. Now let's see. Let's say for example, ammonia is your efficient in this cycle. If ammonia is coming out like this, okay, so if ammonia is coming here, what we'll do is we will keep readily some amount of water. Okay, so we have water, so this forms NH3H2O, because ammonia gets mixed in this water actually. Okay, because whatever the ammonia is coming, because of the presence of water here, this ammonia will be taken directly to this water. Okay, and one thing that you have to understand here is, normally we can see, I'm not going bit of details into chemistry, but right now we can see amount of substance dissolved, amount of substance dissolved in absorbent, amount of substance dissolved in absorbent is inversely proportional to temperature actually. Okay, so is inversely proportional to temperature. Clear? If temperature is high, then definitely this ammonia molecules will try to get vaporized and they'll again try to go back. Okay, so that's why temperature of this mixture has to be low. So that's why what we'll do, we'll generally circulate some amount of cooling water. We'll circulate some amount of cooling water to keep the temperature low. So this is the circuit which sends in cooling water. It's not directly in contact, but because if they are directly in contact, ammonia will come back down. Okay, so that we don't want. So cooling water, it's like a heat exchanger. Okay, so let's suppose this device is something like a heat exchanger actually, so that it transfers cooling. When it transfers cooling water, this mixture, liquid mixture, will get very low temperature. Now when this liquid mixture gets low temperature, we'll use a pump. We'll use a pump actually, because pump work is very small, so we will use a pump actually here, pump, and compress this to some higher pressure, which is pH actually. So this is pH. So using pump will actually send this to high pressure. Here also we have NH3 ammonia, of course, NH3 and ammonia. So we will send this from this to this, from this PL to pH using a pump. And the reason why we are using pump is because the work required for the pump will be much less as compared to the work input to the compressor. You have seen in Rankine, Breton, all these cases. So pump is much effective. Now what you'll do again here, by bringing some source which is, let's say, TS, for example, if there is some source which is TS, and using this TS, we'll do certain amount of heat supply to this. Okay, so when you do heat supply, and you might have studied something called rectification in your schooling, where there is a chemical device which separates the liquids depending on boiling points. Okay, so distillation, rectification, all these things you might have studied. So there is a rectifier here, rectifier. There is some rectifier here. Okay, so this rectifier, what it does, depending on the difference in the boiling points, it will send this ammonia here directly. So ammonia flows in this direction because it separates. So this ammonia goes here, but this ammonia which is going is already at high pressure because of this pump. Okay, and the least or less concentrate ammonia mixture will again come back like this. Okay, so this will come back. Substance which is coming back is low concentration ammonia plus water, because already because of this rectifier ammonia is going. Now in this water which is coming back, this water will actually have this water will actually have very less concentrations of ammonia, but this is actually at high pressure because of this pump. Now you will use a expansion device. This is a complicated mechanism actually slightly. So you will use a expansion valve and you put back this water with low concentration ammonia inside. Okay, so this is the absorption technique. And sometimes what you do, since this water which is coming have high temperature, you will use a regenerator so that some heat gets transferred from here to here so that you can save the heat here. Okay, understood? So because of, like we have done the regeneration in case of Bertrand cycle, you will actually put a regenerator here so that when this hot temperature water is coming, it's like a heat exchanger again. Okay, so some part of the heat gets transferred from this location to this so that the amount of heat what you are supplying at this point will actually come down. Understood? Okay, so this is how the cycle is being maintained. This part is same, but the pressure increasing mechanism in this case is due to this absorption technique. That's why it is called vapor absorption refrigeration system, VARS. Clear? Did you all understand this? How we are doing? We are not going much into the chemical details, but mechanical details is this. Okay? Clear? And normally if you see the COP of this COP of VARS system, if you go into mathematical details and if you do the derivation, you will easily find out this is 1 minus T0 by Ts, where Ts is this source temperature and T0 is this temperature at which it is operating, and TL is this condition. So into TL by T0 minus TL. This is what you get. Okay, means if you assume a heat engine working between this source and this T0 conditions, and also a refrigerator between TL and TL, this is thermal efficiency of the heat engine between these two, and this is COP of the refrigeration between these two temperature limits. Okay, so normally you have to do a bit of maths and all to get this, but first law, second law, all this you have to apply again. But without that, I'm just giving you this formula, COP of VARS. Please try to see, because time is a bit short and all. So right now we can see COP of VARS is this. Okay, so this is product of thermal efficiency. This term is nothing but your thermal efficiency operating between the source and atmosphere, heat source and heat rejection, and because heat whatever is added to the system at this point is deleted here. Okay, so that's why it's like a heat engine working between this Ts and T0, and refrigeration at the end is happening between TL and T0. So this is COP of refrigerator actually. Okay, so this is the product. Clear? Yeah, this is yeah, so normally you can do this, not a very big stuff, but again it takes certain some 10 to 12 minutes time to do all these things. Okay, so that's why I'm just giving you this expression, so that normally this TS is also called TG sometimes, because this is normally called generator. I'll just tell you, this is normally called generator because some heat is getting generated inside, and that is actually sent in because of combustions of what. So sometimes this TS is also denoted with TG. Okay, so TG terminology can be different, maybe notations can be different, but this is the basic idea. Okay, so this is how we calculate the COP of VARS. Clear to all of you? So please type in the chat box, is this clear to all of you? Did you all understand how we can do the compression from PL to pH by converting it to liquid and using a pump so that WC gets decreased drastically? Okay, in previous case only simple compressor is there, but now a bit of complicated mechanism is there so that it works out. Okay, yeah, so let's go to the gas refrigeration systems. So clearly this is the working fluid which acts inside. Now this one standard cycle for this, again you can see we cannot do isothermal combustions on this, so Carnot can be avoided, like how I have shown you in the Bertrand cycle. So similarly in case of gas refrigerations, normally in case of aircraft engines and all we use this. The ideal cycle is like this is reversed Bertrand cycle, like how we have reversed Rankine for vapor, for gas reversed Bertrand cycle. This is also called reversed Joule cycle, or this is also called as Bell-Coleman cycle, which you might have studied sometime. All these are the names for this. Okay, so clearly everything is same, just only one thing, COP. Okay, so if you see, normally if you plot TS diagram, in case of Bertrand cycle you have seen isentropic compressions 1 to 2 here. Okay, then 1 to 2, then you have 2 to 3, 3 to 4, and 4 to 1 actually. Now in this case Just the only thing that differs is these numbers. Normally you can put numbers in any way, but the direction of the cycle is reversed. 1, 2, 3, 4. You can see this is 1, 2, 3, 4, and the cycle happens in this way clearly. And again, you have the compressor here, work of compression, work from the turbine normally, and heat addition here and heat rejection here. That's it. Okay, so all derivations, whatever we have done in Brayton cycle, everything remains same. The only thing is COP. Like you all know, thermal efficiency is equal to 1 minus 1 by Rp power gamma minus 1 upon gamma actually. So if you want to convert as COP of this refrigeration cycle, this is 1 by thermal efficiency minus 1, because you know this gives you COP of the heat pump, and COP of heat pump minus 1 is nothing but COP of the refrigeration plant here. Clear? So normally this is used in aircraft refrigeration. So this is used in aircraft refrigeration. Aircraft refrigerations, because normally you see in the aircraft we have to produce certain temperatures which are low actually. So this is the cycle which is used, and you know much analysis of this cycle I have already given you in the case of Brayton cycles. Okay, so the main thing that's important here is VCRS, because in VCRS again if they try to ask you some questions, it turns out to be lengthy because of this complicated mechanism. So majority of the questions in GATE, even YU or PYQ, you have all questions with respect to this VCRS. Okay, so this VCRS is actually important a bit, so please go through these things. Okay, and gas refrigeration systems, this is the ideal cycle that we use for the case. And normally to make you do some calculations and all, what they do, they'll generally give this isentropic efficiencies for compressors, turbines, all these things. Okay, like how we have done in case of you know our this Brayton cycle in the case of power producing gas power cycles. Similarly, they can give you some amount of isentropic efficiencies for compressors and turbines, so that you can work with the things accordingly. Okay, so is this clear to all of you? This is how we calculate COP. Okay, and now if RP increases, if pressure ratio increases, what happens and all, you can decide. See, if pressure ratio increases, clearly you know thermal efficiency increases. Okay, if thermal efficiency is increasing, then this value will fall, so COP will fall down. Okay, because eventually this compressor will require more work for the same amount of heat interaction. Okay, let's say if I increase the pressure ratio without changing this H1 and H4, then definitely refrigeration effect remains same, but your compressor load increases. Okay, let's say for example if I draw the curve like this, and if I do this part, then H1 minus H4 is not changing. Okay, but this curve actually changed. That's why, so COP will actually come down in that case. So could we do some questions tomorrow? I'll do one thing. I'll put one question today. Maybe I got some questions. Yeah, come on, do this question. Reversed Carnot cycle used for chiller plant works between minus 33 degrees Celsius and 27 degrees Celsius when it's in winter. If the plant produces 10 tons of ice per hour in winter, then the amount of ice produced in summer when environment temperature increases by 10 degrees is dash tons in 1 hour. Is dash tons per hour. Is dash tons per hour. Come on, do this question. Quick, I'll connect a poll maybe. So integer type, whatever the answer you get, enter the nearest integer. Okay, so I'm giving you some time of 120 seconds. Come on, do. I think we cannot start refrigeration, air conditioning today also. But refrigeration is 100% clear to all of you. Anyway, I think you are busy in solving this question. Come on, solve. Come on, all of you solve this question. See, basically in winter, what's happening? Temperature, the atmospheric condition is decreasing. So it is 27 degrees Celsius in winter, so it would be 37 in summer. That's it. Okay, 8.57, is that the answer? I don't know, we have to work it out. 8.6, yeah, I think all of you may be correct, because in last class what happened with the compressor stages question, all of you gave the same wrong answer. Okay, so but anyway, let's see, this time I guess you are correct. Let's work it out. Okay, solution. So let's see, a reversed Carnot cycle for chiller plant works between minus 33 degrees Celsius and 27 degrees Celsius when it is in winter. Okay, so reversed Carnot cycle, so therefore COP is equal to Q dot L divided by W net actually. Okay, so what happens, you are using the same compressor, same power, whatever. We could be wrong. No, I wish you are correct this time. Okay, so this is what you have. So in the first stage this is the case, and in the second stage we have COP in the second case is equal to Q dot L divided by W net 2 actually. Okay, so this is W net 2. Now one thing that's clear is this Q dot L is proportional to mass of ice produced. Yes or no? Mass of ice produced, because normally the plant inlet conditions all will be same. Okay, so water will be coming at same temperature, all these things. So efficiency, sorry, didn't get this. So efficiency used where here, because it's a chiller plant, no, it's a reversed Carnot cycle, correct? So let's see, Q dot L is proportional to mass of ice produced, and depending on the power input and the compressor, definitely what happens, this W net is same in both the cases, because they haven't changed any environmental I mean they haven't changed any this compressor working conditions. So COP1 by COP2 is equal to, because this is equal to Q dot L in the first case by Q dot L in the second case, but Q dot L is directly proportional to the mass of ice produced. So mass in the first case by mass in the second case. Okay, so anyhow it is given in terms of tons, so let's put both in tons. So let's see, COP in the first case, the temperature is minus 33 and here it is 27. Okay, so in the first case the thermal efficient this COP is TL, so TL 273 minus 33 240 divided by this TH minus TL 27 and 33, summation is 60, divided by, coming to COP in the second case, if temperature outside increases by 10 degrees, okay, that still stays at minus 33, so 240 divided by, then this temperature increases by 10, so this is 37 plus 33, it is 70, then in that case is equal to, initially some 10 tons of ice is being produced divided by X. We don't know how many tons is getting produced this time, so 240, this gets cancelled, so X is equal to, this is actually 7 by 6 is equal to 10 by X, so X is equal to 60 by 7, that's it. Okay, so these many tons is produced actually. Okay, these many tons is produced, clear? So 60 by 7, roughly 8 point odd, because you can see 7 8s are 56, so 7 8s are 56, 8.40, so 5s are 35, 57, that's it, roughly 8.57 tons is what you are getting. 8.57 tons, yeah, 8.57 is the correct answer. Good, yeah, 8.6 if you round off to one decimal, it is 8.57 or 8.6, whatever, depending on number of decimals you are rounding off. Did you all understand this? Simple calculation, nothing big. Okay, now let's go to the next question. Come on, solve this question. The power required to drive the plant is dash kilowatt. Maybe again you can enter, this is roughly 9 you have entered, many of you, let's see, or 8 you might have entered, right? It's okay. So solve this question. A cold storage is to be maintained at -5 while surroundings are at 27. Heat leakage from the surroundings into the cold storage is estimated to be 29 kilowatts. The actual COP of the refrigeration plant is 1/3 of the ideal plant working between the same temperatures. The power required to drive the plant is dash. Come on, do this. Again, enter nearest integer. So I'm putting, say, fine, okay, 120 seconds again. Do. Come on guys, quick. You guys can do it faster. There's a cold storage which is maintained at -5 outside atmosphere is also there. Heat leakage from outside to inside space is 29 kilowatts. COP of the plant is 1/3 of the ideal plant COP. So what is the power required to drive the plant? Come on, time is running up fast. $10.38 is coming. Okay, it is poll is running. If you are getting 10.38, you can enter 10 as the correct answer. Okay, because here we don't have decimals to give you as of now. 10 is what you have entered. Okay, let's see. Even I don't know the answer, we have to work it out. One thing I know is definitely it should be less than 29. That's all I can say as of now. Okay, fine. Anyway, let's see. Now there is a cold storage plant. Cold storage plant. Now from this cold storage, you have to maintain this cold storage at what temperature? At 27. Okay, so you have to maintain this at 27 degrees Celsius. If you want to maintain this cold storage at 27, definitely what you should do, whatever is the heat that is flowing in, the heat leakage from the surroundings is 29 kilowatts. So let us say if this is heat leakage, that should be the same amount which you should take out using your refrigeration system. Yes or no? Means the amount of heat your refrigeration system should take out is same as whatever is the heat coming inside. Only then steady state, na, if this has to maintain at same temperature, heat coming in should be equal to heat flowing out. Okay, so heat coming in should be equal to heat out, and QL has to be equal to Q out. Actually, for cold storage to be at 27, degrees Celsius, definitely your QL has to be equal to Q out actually in this case. Okay, so QL has to be equal to Q out. Now COP is equal to Q dot L divided by W dot in. So they are asking what is the work input, power required to drive. So W dot in is equal to COP of the plant is equal to this. So W dot in is equal to Q dot L by COP of the plant. Now what is COP of the plant? First of all, Q dot L is same as 29 because that's the amount of heat which is coming in. So COP of the plant, is 1/3 of its ideal plant. Okay, so which is Q dot L divided by 1/3 times of COP of this. So 5 we have to, at 5 we have to maintain. Sorry, didn't get you. At 5 we have to maintain. Matlab we have to maintain at 27, na? That's what they have given. While the surroundings is at -5 is what we have to maintain. Okay, fine, got it. Yeah, this has to be maintained at -5. Correct. -5 degrees Celsius is what we have to maintain. Okay, so 1/3 times of COP of the plant working between these conditions. Ideal COP is -5 is the temperature of the plant, so definitely this operates at -5. So -5 is 268 divided by 27 and 5, 32. So this is the COP of the actual plant, and this Q dot L is nothing but 29 kilowatts. That's it. If you do this, you will get this power input, and this is in kilowatts, so the answer is also in kilowatts. And what are the units they were asking? They were asking in kilowatts. Good. So this is the value. So let us do some calculation a bit and let us get the answer. So what we can do, let us multiply directly now, better. So 32, this is 134 and this is 16. So 29 into 48 by 134. 29 into 48 by 134. Okay, so 10.388. 10.38 kilowatts roughly. Okay, so 10.38. So you might have entered as 10 here in this case. Okay, so anyway, 10. Let's see, show results. Nice. Leaderboard, I cannot see the leaderboard, I guess. Okay, Nitin has answered it correctly in 50 seconds roughly. Yeah, good. Okay, so 10.38, yeah, 10.39, whatever. 388, so 10.39 kilowatts can also be taken. Okay, so these are the things that we can do. And one question on VCRs also I think we have. Yeah, come on, do this question. All of you do this question to 1 decimal place. So maybe again you can enter in integer type 120 seconds. Okay, before starting the poll, let me see. VCR system of 10 tons refrigeration capacity of evaporator, vapor is 9.9% when it leaves the evaporator. Mass flow rate of the refrigerant is dash grams per second. Fine. Okay, I'll do one thing because the time is actually short. You know how to do this because only the one difference that is given. This vapor coming out of the evaporator is having 0.95 dye. Okay, so vapor coming out of the refrigerant is not completely saturated vapor. It is just because the time is actually short. See, the vapor which is coming out is not exactly at the saturated vapor condition. It is somewhere in between. So 0.95 dye. So you have to calculate H1. H2 is definitely will be given to you because you can see VCR system having an evaporator temperature is this. The properties of refrigerant at -10 at 40 degrees Celsius. This is HF and this is HZ is what you have. So VCR system 10 ton refrigeration capacity. Refrigeration capacity is directly given at an evaporator temperature of -10, needs a condenser temperature of 40. The vapor is 0.95% dry. When it leaves the evaporator, the mass flow rate of the refrigerant is dash actually. Okay, so mass flow rate of the refrigerant. So m dot refrigerant into H1 minus H4 is equal to 10 tons. 10 tons is 211 or 10 into 3.5 kilowatts. 3.5 kilowatts. So if you calculate this m dot refrigerant, H1 you can calculate because H1 is 0.95% dye. So H1, what about H1? H1 is equal to HF at evaporator pressure at -10 plus 0.95 times HFZ at -10. Okay, so this is what you have. This is H1 and H4 is same as H3 because 3 to 4 is isenthalpic. So H3 is nothing but HF at 40. So you know these values. HF at 40 is known to you. HF HZ at this condition is known to you. So you can calculate HFZ and HF. If you do these two things and put it here, you will get m dot refrigerant. So H1 minus H4 is equal to 35 kilowatts. That's it. So you put these values in kilojoule per kgs, you will get this m dot f in kgs per second. You will get this in kgs per second. You convert this to grams per second. That's it. Okay, that's it. Clear? So anyway, just work it out these values and tell me the answer tomorrow. Okay, so this is like homework. Of course, I have given you some hint. It's not homework, it's homework. Home, HOME. Fine. Yeah, homework. Okay, so please do this calculation and you can tell it. 35 is coming. 35 grams per second, maybe it could be the case, I don't know, but this is the idea. Okay, so this is the refrigeration effect total. So H4 can be taken as H3, which is HF at this condition, which is 40, for which you have the values 371.47, and just substitute here, you will get the mass flow rate of the refrigerant flowing in the circuit. Okay, fine. So clear? Fine. I thought of doing some psychrometric also today, properties of moist air and psychrometric process, but of course this VCRs has taken some good enough time. But anyway, Joule-Thomson coefficient, because some of you have asked some doubts. So in today's class, basically we are talking about refrigeration. So we were talking about VARS, VCRS, then we have seen cycle performance and all the stuff. Similarly here VARS, we have seen what is the mechanism that's changing from PL to pH, and also gas refrigeration systems. Gas refrigeration systems. Along with this, we have also seen plus some story of refrigerants. Basically we have talked about nomenclature, because that is also important sometimes in some exams and all they are asking nomenclature, and here we have also talked about Joule-Thomson coefficient, 𝐂𝐸𝐴𝑇. Okay, inversion curve, all these things we have talked. So anyway, because of having some short time today, we were not able to start air conditioning, but in tomorrow's lecture I'll start air conditioning. We'll see properties of moist air, why moist air can be treated as ideal, vapor can be treated as ideal gas, and we will calculate enthalpies, omega, DTP, adiabatic saturation temperatures, and applying energy balance. All this stuff we'll do, okay, for control volume analysis. Okay, so tomorrow we'll start air conditioning and we will try to close it tomorrow. It's like a one shot of air conditioning tomorrow. Okay, but are you all understanding the things? Refrigeration, did you all understand it better than your previous knowledge? Okay. So yeah, so fine, we'll meet tomorrow at 4 p.m. and we will discuss on air conditioning. Okay, at 4 p.m. tomorrow. Thank you. Fine. Any doubts? Is everything fine? Okay. Yeah, no questions. Fine then. Thank you. Take care.